Hello, this is Jim Grange. This is an introduction to flankr, which is an R package implementing computational models of attentional selectivity. It's based on work which is published in Behavior Research Methods. Within this paper, I give a full overview of both of the models that flankr implements. So this is the dual-stage two-phase model of Hubner and colleagues, as well as the shrinking spotlight model of Wyatt and colleagues. I've tried to make the paper as accessible as possible to researchers with no programming experience and no experience in computational modeling. So in this video I will just go over the package and you'll get to see it in action. So I'm hoping that this will help users engage with this package for their own use. So I just want to give a very brief overview of the two models that are implemented within flankr. Both of the models are interested in the dynamics of attentional selectivity during performance on a typical Ericsson flankr task. Within this paradigm, participants are presented with a stimulus, such as these arrows. The task of the participant is to respond as to which direction this central target is facing, so they're making a left or right response. They have to make their response as quickly and as accurately as possible. This central target can be flanked by arrows that are incongruent to that of the target, so they are arrows pointing in the opposite direction to the correct response, or the arrows can be congruent, the flankers can be congruent, that is, they're facing in the same direction. It's a very, very robust finding that response times are slower and less accurate to incongruent flankers than to congruent flankers. However, participants are able to overcome the negative effects of these flankers and are able to attend to the central target and respond accordingly on a very good proportion of trials. So the dynamics of how participants are able to filter out the negative effects of these flankers are well demonstrated by so-called conditional accuracy functions, which we have here. So we'll just focus on these open circles, which represent data from incongruent trials. So we can ignore these dashed lines here. We'll come to talk about these later. Conditional accuracy functions, this particular one, what it does is it's taken all of the incongruent response times and it's sectioned them into bins, going from the fastest response times to the slowest. So this circle here represents the fastest 25% of incongruent trials. What we do is we calculate the mean response time for these 25% of trials, and we plot this against the accuracy for this 25% of trials. And then we do the same for the next 25% and so on until we've got all of the response times accounted for. So what we can see is that when participants are responding very quickly, at least within the 25% of their response times, accuracy is relatively low. But at slower response times, this accuracy has improved, almost to the same level as congruent response times. So accuracy seems to improve as participants are exposed to the stimulus for a longer time. And it's this improvement of attentional selectivity with time that both of the models that I'm going to discuss are interested in. So what is the dynamic of this improvement in attentional selectivity? So the first model that's implemented by flankr is the dual-stage two-phase model of selective attention published by Ronald Hubner and colleagues in Psychological Review 2010. Within this model, it's assumed that response selection is governed by a so-called diffusion process, represented by this black line here. This diffusion process represents the accrual of evidence towards one of two particular responses. So it's a model of two-choice response time, which is the case in a flankr task. So this upper red line represents a response boundary for the correct response, and this lower red line represents the response boundary for the incorrect response. So if this diffusion process hits this upper boundary, it's assumed that the model has made a correct response. However, if the diffusion process hits this lower boundary, then it's assumed that the model has made an incorrect response. In this model, response selection has two particular stages to it, a first stage and a second stage. So this vertical dashed line here demarcates when the model switches from the first stage to the later second stage. In this first stage of response selection, it's assumed that the drift rate is influenced by all elements in the stimulus display. So you'll actually see here In this case, the diffusion process is actually heading towards the incorrect boundary, and that's because the model is processing information from these flankers, and so therefore the diffusion process steadily marches towards the incorrect response boundary. However, at a particular point in time, the model successfully selects a central target for further more detailed processing. So once the model has selected a single element from the display for further processing, response selection enters this second stage. The diffusion process now is solely governed by whichever element has been selected. In this case, the model has successfully selected the central target for further processing, so therefore the drift rate marches more steeply towards the correct response boundary. How long it takes the model to select a single element from this display for further, more detailed processing is governed by a separate diffusion process that runs in parallel to the response selection process. So in this diffusion process, there are also two boundaries. If the diffusion process hits this upper boundary, it's assumed that the model has selected the central target for further processing. If this diffusion process hits the lower boundary, it means that the model has erroneously selected one of the flankers for further processing. You'll see the point in time in which the model has selected an element from this display for further processing is the time point at which the response selection switches to its second stage of processing. So this is the main idea in the dual stage two-phase model, that at early stages of response selection, attention is being influenced by all of the stimulus display. However, at a discrete point in time, the model selects one element from the target display for further detailed processing, so therefore response selection enters this second stage. The second model that flankr implements is the shrinking spotlight model of White and colleagues, published in Cognitive Psychology 2011. Within this model, response selection is also occurring via a diffusion process where we have the same two response boundaries as before. So a response boundary for a correct response and a response boundary for an incorrect response. However, the dynamics of improvement of this drift rate towards the correct response boundary occurs via a very different process than the dual stage two-phase model of Hubner and colleagues. In the shrinking spotlight model, it's assumed that at early stages of processing, response selection is governed by the whole stimulus display. So this dashed line, can be considered the attentional spotlight. However, as time progresses, the attentional spotlight gradually starts to focus in on this central target. So the elements falling within this attentional spotlight are the elements that are contributing to this drift rate. So as time progresses, the drift rate becomes more and more dictated by information coming from the central target display. So that is why you get this improvement in the drift rate towards the correct response. So if we're looking at the schematic of this attentional spotlight, we can see the direct contrast between the shrinking spotlight model on the right and the dual stage two-phase model on the left. So the shrinking spotlight assumes that attentional selectivity improves in a gradual fashion, whereas the dual stage two-phase model assumes that attentional selectivity occurs at a very discrete time point, before which response selection is governed by the whole stimulus display, and after which it's only governed by the central target. So because these models are implemented computationally, the models have so-called parameters. These parameters reflect certain aspects of the processes that I've just discussed. So I'm not actually going to go through these parameters or their descriptions in this video, but of course you can see discussion of this within the paper itself. So flankr is a package that extends R statistics, which is a free statistical programming environment. So if users wish to use flankr, they'll also have to install R onto their machines. In the paper, I've also recommended that users install RStudio, which is just a nice interface to use R with. So this is also free. To install R, you just need to go to r-project.org and then click on the download button. You need to select a so-called mirror that is close to your geographical location, and the installation is relatively straightforward. To install RStudio, go to rstudio.com and select Download RStudio. Both of these pieces of software are available for Windows, Macintosh, and also Linux. flankr itself is available on github.com. However, if you just wish to use flankr, you'll never have to access this site at all. But the address is here for users who may wish to access the code to modify it or extend it at a later date. But as I said, if you just wish to use flankr just to fit your own data, there's no need to access this whatsoever, but it is available should you so wish. Okay, so what we're going to do now is launch RStudio, and then I'll walk you through a little bit about how to use RStudio, and then we'll get straight into how to use flankr. Okay, so this is RStudio. This is what you should see when you open it. So we have a command console over here on the left, and then these two windows here will be blank. The upper one will contain data as we start to work through examples of flankr, and then when we come to do plots, they will appear here in the lower right. So we enter commands on this command line, which starts with this right-facing arrow. Any command we enter here will be interpreted by the R programming language and executed accordingly. So for example, we could enter 2 + 2, hit return, and it gives us the solution 4. Now, when you're using flankr, it's fine to enter commands one line at a time in this console, but I always find it much nicer if you enter commands into a script. Then you can save your script and access it again at a later date. So to launch a new script, you just click on this blank page button here and select R script, and a new window appears here. So in this window we can enter commands also, but you'll notice when we hit return they are not executed. In order to execute any commands we enter into a script, we highlight it just by clicking and dragging and then clicking this run button. And now you'll see this has been executed down here at the bottom. So what I've done is I've prepared a script that contains some key functions that allow the user to use flankr. So what I'm going to do is I'm going to open this and then walk through it with you just to show you what each aspect is doing. So I'll make this available for download for you at a later date. Okay, so one thing I will do is just increase the font size just so you can see it a little bit better. Let's increase this to 12. Okay, that's a little bit better. So any element within a script that is preceded by a hash mark is a comment. So if you were to select this and click run, nothing happens. So R just ignores anything that has a hash mark before it. So before you get started with flankr, you have to install two packages. The first package that needs to be installed is the DevTools package. So this only needs to be done the first time that you wish to use flankr. So all you do is you just highlight this and click run, and what that do install the free package DevTools that then later allows you to install flankr directly. So I won't do this now because I actually have this installed. Now what you need to do is install the flankr package itself. So this comes from my GitHub account. So what we're telling R to do here is to install from GitHub within my repository the files associated with the package flankr. So if you highlight this and select run, that will install flankr to your system, making it available to you to use. So this might take a little while to install, so I just paused the video just whilst it installed, and it took about 60 seconds or so. Once everything has been installed, so now we have flankr installed, we need to enable its functionality for this particular session. So every time you start a new session and you wish to use flankr, you have to tell R to make it accessible. So you do this using the library open parentheses flankr function. So if we just highlight this and click run, what this will do is it will now make it accessible, so we can now use all the functions within flankr. So the first thing we'll have a look at is how to simulate some synthetic data from the models. The only examples I'm going to go through are for the DSTP model. The only difference between functions for the DSTP model and the SSP model is that we'll just add SSP to the end instead of DSTP. So if we wanted to simulate data from the shrinking spotlight model, we would just change this to SSP. And then it would work just the same as what we're going to go through now. If you want to look at any help files for a particular function, just enter the question mark and then the name of this function and just run it, and then you'll get some help information up here on the right, such as what values that you need to be entering, how to adapt the function, etc. Before we're able to simulate any data, we need to tell flankr which parameters we'd like to generate some data for. So see table 1 in the paper for a description of the dual stage two-phase model parameters and also the order in which to enter them below. So the DSTP model has 7 parameters, so we wish to tell flankr that the parameters we want to use are these particular values here. So obviously these can be changed by the user just by highlighting and just changing. So if we highlight all of these and click run, these parameters are now stored in a variable called parameters, and we'll later access this when we're using the simulate function. So now let's simulate the data. This uses the function simulate DSTP. Arguments that we pass towards this function, we need to tell the function which parameters we want to use. So we say parms equals parameters, because you'll see one of the arguments that we need to pass to the simulate function is parms, and also how many trials we'd like to simulate. So in this case we're saying we'd like to simulate 1,000 trials, so this will produce 1,000 congruent trials and 1,000 incongruent trials from the model with these particular parameters here. And what we're going to do is we're going to store this data in a variable called DSTP data. So if we highlight all of this and click run, that will then simulate the model using these parameters and store the output in this variable here. So you'll see we now have this data available here. If we wanted to look at it, we could just type in the name of the variable that we've just used, so DSTP data. But you'll see it's quite unwieldy. We've got 2,000 rows. So if we just want to look at the top of it, type in heads, open brackets, then the name of the variable that we've just used. We'll see that this function has returned 3 columns, one containing the response time for each trial, one containing the simulated accuracy for that trial, and just the congruency for the current trial, whether it's congruent or incongruent. So this is just a neat way if the user wishes to simulate some data with known parameters just to see the model's behavior. So the next function we want to look at is how to actually fit the model to some human data. So the flankr package comes with some data that you can use to explore the fitting routines for both models before you actually use your own data. So if you wish to use this, we first need to tell R to load this data. The data is called example data, and to load it we just need to run this particular line here. So let's look at the data. As I said before, the head function shows the column headers in the first few rows of the data. So we'll see that the data file that comes shipped with flankr contains several columns, one containing subject identification information. The third column contains the congruency information, then we have accuracy and the response time in seconds for each trial. But in this particular data, I had 2 additional conditions on top of that of congruency. So before the flankr stimulus was presented, I either played a short warning signal through headphones to the participant, or I did not play that warning signal. So this column here is just coding for whether this warning signal was absent or present. And this is because sometimes you will have some flankr data where you have an additional a factor other than congruency. So now actually let's fit the DSTP model to this example data here. When you're fitting the models to some data that you have. If you do have a condition over and above that of congruency, you can only fit the model to one condition at a time. So you cannot fit the model concurrently to absent and present. We'd have to run two separate fitting routines, one for the absent data and one for the present data. It should be added that each fitting routine simultaneously fits incongruent and congruent data, so we don't need to separate these, and in fact you can't with flankr, but you do need to separate out your fits to additional factors. So when we're fitting the DSTP model, we use this fit DSTP data. So if we want to look at a help file for this, remember we enter the question mark and then the name of the function. So let's highlight this and click run. We'll see that there are quite a lot of arguments that might need to be passed to this particular function. Not all of them are essential because some of them have default values, and I'll refer you to the paper for more advanced use of this particular function. But in this case, we just want to fit data from the present condition. So here we're using most of the default function values that are in this particular function here. So we want to store the fit to a variable called fit_present, because this is the condition that we're currently fitting when the warning signal was present. We use the fit DSTP function. We need to tell the model which data we're using. So we're using example data. So we say data equals example data. And which condition are we fitting? We wish to currently fit the present condition, so we say condition name equals present, and this needs to be within speech marks here. So if we highlight this and click run, the model will be fit to this data, and the outcome of the fit will be stored to the variable fit present. Now this routine can take a little while, so what I'll do is I'll click run. So the model is now being fit. This will take a little while, so what I'll do is pause the video and then return once it has finished. Okay, so the fit has finished. Once it has finished, flankr will tell you that it's done so, and also you'll see now we have fit present, which is the variable that we asked details of the fit to be stored to. So if we want to look at the details of the fit, we can just type in the name of the variable that we used. And then what it does is it returns three pieces of information. The first one is just the values of the best fitting parameters found by the fitting routine. And then we have the fit statistics g², and the binned BIC values. So these are described in more detail in the paper. Now, of course, once you've fit the model to your data, it might be nice to actually just have a look at how well the model has fit your data. So you can do this by using the plot fit function. So because we're using the DSTP model, this is called plot fit DSTP. We pass to it a few arguments. The first one is the variable in which we've stored details of the model fit. So this is stored in the variable fit present. So we do model fit equals fit present. Also, we tell the function what the data is that we were fitting the model to. So it was example data, and also the condition that we were fitting. So if we highlight all of this and select run, it will take a couple of seconds. But here on the right hand side, now we will see details of the fit. So on the right hand side, we have the conditional accuracy function, which I described earlier. We have in the circles represent the human data, and the lines represent the predictions of the model. So these are the model fits here. On the left, we have cumulative distribution functions, which are also described in the paper. This is just showing the difference between congruent and incongruent response times throughout the whole response time distribution. So the fit looks pretty good, but what we might want to do is try different starting parameters for the fitting routine. So the best fitting parameters can sometimes change depending on which values you use to start the search routine. So let's try using some different starting parameters for the fitting routine. So what we'll do is, let's say we want the fitting routine to start from these values. We'll use these as the first best guess, and then the fitting routine will dynamically update these values to try and improve the fit. So we can store these values in a new variable called new palms. So we'll just run this. And then what we do is we'll run another fit, so another pass to the fit DSTP function. But you'll see now we're using a new argument passing to this function called parms. So this is allowing the user to change the starting parameters that the fit routine uses. So we want these parms to equal new parms, which we've just defined here. So I'm not actually going to run this just to save a little bit of time, but you can explore this as you're going through this script. And then what you can do is just plot this new fit that we've used to the data. So I should also add that whenever you run the plot fit function, not only does flankr return visual overview of the model fit, it also returns within the dashboard the numerical details that go into making up these plots. So if for whatever reason you don't like the plots produced by flankr, you can use this data to generate plots using whichever software you want to use. So the other function that I'd like to briefly discuss is the fit multiple function. So in this case, the fit multiple DSTP function. We've just discussed how sometimes you will want to change the starting parameters that's used for the fitting routine. So it might be the case that you actually want to explore multiple starting points to the fitting routine, and I describe why you'd want to do this, or why you might potentially want to do this in the paper itself. So flankr allows you to do this relatively straightforwardly using this fit multiple function here. So what the fit multiple function does is it will generate lots of random starting points around a particular set of predefined parameter values. So what we want to do is store these particular parameter values in a variable called current parms. So current parms represents if you want the average of the set of starting points that we're going to use to explore the model. So these represent the average values. Then what's going to happen is this fit multiple function will generate multiple variants of these starting points here, and will perform the fitting routine for each of these different starting points. So let me break this down a little bit further. We tell the function how many sets of starting points we'd like to use. So in this case, n parms equals 20. What this means is that this function is going to generate 20 random permutations or random variants of this set of parameters here, and use each one of those 20 as a starting point to the fitting routine. So it's going to do the fitting routine for each of these 20 starting points, and then it will return the best set of parameters found across all 20. You can vary how far the function will stray away from these mean values using the var function. So in this case, we're using a relatively low number of 10. So the random starting points that are going to be generated are going to be relatively close to these values. Again, I discussed this var argument in the paper itself, so I'll refer you to that for more information. So if you run this, it takes a lot longer because obviously you're using a lot more starting points. So to reduce the time, you could reduce the number of trials it's simulated on every trial to maybe 5,000, and then run this, and that will produce a best fit from multiple starting points. So if we click run, so this will start running now. So again, I'll unpause the video when this has completed. Okay, so now the model fit has finished. We can look at the details of the best fitting parameters. So if we highlight it and select run, we'll see now these are the best fitting parameters returned after searching through 20 different sets of starting points. We'll see we've got the G-squared statistic and also the bend BIC statistic here. So again, what we can do is we can plot the fits of this particular fitting routine. Make it a little bit bigger here. Just in the same way as we did before. What you might want to do now is, because we have conducted a broad search of possible starting parameters, you may now want to conduct a final fitting routine using the best fitting parameters from that broad search. So to do this, what you can do is you can access the best parameters from the previous fit. So remember, this previous fit was stored in the variable multifit. So let's just look at this again. You'll see that the best parameters are stored in a sub-element of this variable called best parameters. So we can access this using the $sign and then the name of the element that we want to access. So if we just highlight multifit $best parameters and click run, we can extract what the best fitting parameters were. Now what we can do, we can use these best fitting parameters as the starting point of another fitting routine and boost the number of trials that we simulate. So this will just present just a slightly more refined parameter search routine. I should say I suggested this in the flankr paper in behavior research methods, but I haven't really seen this method being used, at least it's not reported being used by other researchers. But the problem of finding the best parameters and the problem that best fitting parameters can change depending on which starting parameter you use is a problem that's common to all computational models. So this is just one solution which I found to work relatively well, although I'm sure there are others that you'd be able to implement using flankr. Okay, so that was just a broad overview of just some of the core functionality of the flankr package, so I hope you found it useful. So if you have any problems at all with this package, or if you have any questions about how to use it, then please do contact me on the email address. So I really do want this package to be as accessible as possible to all researchers. So if you're finding any aspect of it unclear, then please don't hesitate to contact me, and I will do the best I can to resolve any questions that you have. So I hope you find it useful, and thank you very much.